excited to see the community here. I think we've all been interacting since yesterday, and it's been great to meet all of you. So I'll just start with a brief introduction about myself. I am Mohit. I work with Amazon. I am a senior software development engineer there, and I've been contributing to OpenSearch since the inception of the project. I mostly work in the areas of indexing performance and also indexing features and some search-related performance as well. So yeah, just to get started, right? So today we'll be covering something in the area of how we have basically had a journey of analyzing OpenSearch's indexing performance and mostly making improvements to that. But before we go there, I'll just start with how OpenSearch indexing actually works. So I think the diagram is a little containing too much information, but yeah, so whenever client sends a request, right, the request will arrive on the coordinating node, and at the coordinating node, the decision gets taken where the request should go to. So when you configure index, you create multiple shards for it, right? And the coordinating node decides which shard should this document go to based on the _ID field or the routing parameter you provide. Once the document is a primary shard, the node containing the primary shard, we do a few operations. First, we actually parse the document. So say in the indexing API, you sent a JSON, right? So that JSON gets parsed field by field and value by value. And then for each field, as we are passing through the document, we create different Lucene fields. And as those Lucene fields are created, we also run analyzers post that, so that let's say you have a text, you want to run some white space analyzer, n-gram analyzer, all those runs. And then your data gets actually indexed into the Lucene. And at this point, your data is only in the in-memory buffers of Lucene. It's not been persisted yet. So we do have something called as a write-ahead log, which is the translog. And the documents would go to that translog. And once the documents are persisted there, right, in the translog, it's f-synced to the disk. And you are sure that even if the process goes down, you can recover the document. That's when you say that the document ingestion is finished on the primary shard. And then to ensure that, OK, even if this node completely goes down, right, you're not able to access it, we do have replication in place as well. So this diagram shows the document replication flow as well. So the same flow, once the document is completely ingested on the primary shard, it will go to the replica shards, and there we'll follow the same process. We have something called as segment replication as well, which doesn't require you to reindex the document on the replica shards, but I'll keep it out of scope for now. And once all this document basically ingestion on primary and replication is finished, we return the success response back to the users. And after this indexing has been performed, there are a few background operations which keep on happening as well. So we saw that we had only added the documents to the in-memory Lucene buffer. What we do is, in the background, we actually flush all the documents to the disk as well. So basically, the data structures that we would have created, right, they are made persistent on the disk. And there are a few other operations like flush, apart from flush, refreshes, merges, which we'll cover later as well as we go through some features. So once your index is created, right, you just sent a JSON document, but it can translate to a lot of files behind the scenes. So for example, if you have term vectors enabled for your text fields, right, it will create these files. Stored fields is one of the most important data structures that we also use, because the entire source you pass, right, for the operations, like when you want to retrieve the document back during your queries or you want to reindex, the stored fields contain the entire source that you would have sent and stores it. Similarly, we have a numeric index for queries which are based on numbers, inverted index, which is the most powerful feature of Lucene and OpenSearch, which basically is the entire inverted index on the text fields. Then we have some metadata files as well, segment info, which contains information about what this segment contains and all, field names. And then there is a live docs file, which contains information about the deleted documents. And then we have a segments_n file. This is kind of like the commit point file for you. We do also have some columnar data, which is used for purposes of sorting, aggregations. And then we have KNN vectors as well, which is, I think, the most hot topic in the market today. So yeah, now that we know how the on-disk data structure looks like, right, just to give you an overview, for web access logs data similar to what I've shown here, if you had to ingest 8 TB of data on a 4 vCPU, 3 data node setup, it would have taken almost 3 days. And the data would have become almost 1.5x times of what you would have provided, basically the uncompressed data that you would have provided. And this adds a lot. Basically, there is a lot of compute going on, storage going on. And in order to basically translate the cost improvements and performance improvements to the users of OpenSearch, we have done a lot of improvements, which I'd like to cover next. But before that, let's analyze how we have come together to see what performance improvements can we do. So few of the areas we explored are like throughput and latency improvement for the entire indexing process. Then there is storage cost reduction, the replication costs that are involved, for example, the segment replication that I talked about. Then making the background operations faster, because they also consume CPU and memory, right? So how can we make them faster and more efficient? How can we introduce new data structures for faster querying? So essentially, your indexing can be fast if you don't create any data structure, right? You don't have to do anything. But at the same time, how can you index in a way that you are able to query faster? So we have explored those areas as well, and also towards improving the accuracy of results. So coming to indexing, right, from the flow we discussed earlier, there are few things that we have focused on. So data ingestion, which basically covers the data coming from users to basically the coordinating node. There is document parsing, which is, again, a very time-taking process. The document replication, because it provides you high availability and durability, but it comes at its own cost. Data storage, because as you have to basically make your queries faster, you won't want to basically bloat your storage as well, right? You want to keep your storage minimal while trying to serve the query in the same performance. And a few runtime improvements also, which in general help us improve the OpenSearch process. So yeah, just to cover a few, right? So a few of the optimizations that are already present in OpenSearch, starting in OpenSearch 2.x somewhere. So one of the improvements that we did was around fast double parsing. So instead of JDK-based double parser, we went back and looked into other parsing libraries. We went and looked into a few of the papers, and we came across a novel technique which helped us parse the double numbers faster. And just for use cases like metrics and all, right, where you have things like latencies, bytes received, and all those things, it helps a lot because the higher the number of fields you have which are floating points, it helps with the performance improvement if this improvement is applied. And essentially, it helped us with the overall 5% throughput improvement in data set like NYC taxis. Similarly, we implemented a faster datetime parsing. So JDK's datetime parser is built in a generic way so that it can support a lot of use cases. But for most of the use cases where, let's say, you are using an ISO 8601 kind of format, right, or some specific format, you can optimize based on the strictness or leniency of how you want to parse the datetime. So based on that also, and that is always going to be present in a log analytics or time series kind of workload, right? So just applying this faster datetime parsing, it helps us with 5% more throughput improvement. The third thing is the custom codecs through ZSTD. So by default, OpenSearch uses LZ4 as its compression algorithm for the stored fields. So stored fields, as I talked about, stores the entire document source. And if I can improve on that, right, it helps me with a lot of storage reduction. So for example, generally the stored fields or the actual source takes about 30 to 40% of your data storage. And improving on that helps me with almost 35% storage reduction. And because I can compress better through a better algorithm now compared to LZ4, ZSTD provides me 14% throughput improvements as well, and P90 latency is also improved by 5%. One more magic it does is, now that your segments are slower, there is a periodic operation of merges which happen to basically merge the different segments which are created. So the merging process also becomes lesser because you now already have very small segments and you don't need to compact them further very often. So the frequency of the merging also reduces, which gives a lot of throughput improvement in this 14% that we see. Few other things that we did were around reduced allocations during document parsing and translog memory accounting. So whenever you do update operations, right, we tend to look into what was the last version of the document that was present, what were the fields that were present in the document. And as part of that flow, we analyzed there were few unoptimized checks that were happening to account for memory so that we could apply memory controllers and all. And with this, we could improve essentially 5% throughput on the workloads where users were trying to have large translog sizes. So they were not flushing that often. And it was causing a lot of lookups in the in-memory maps. So we could optimize it by changing a few lines of code only. Like it was a 3 to 4 liner code change, and it helped us with almost 5% throughput improvement. So that was quite a good win. And then we also introduced Bloom filters in OpenSearch. So for update-heavy use cases, right, what happens is you want to look at the existing term or the ID, ID against which that document was indexed, right? So that lookup requires you to go to disk, look into the inverted index, and then figure out. But if we have a Bloom filter on top of it, right, it helps you make the decision in memory itself with a good false positive probability. So with this, we could see almost 30% improvements in the performance of upsert operations. And this is available as an index setting for opt-in, and for update use cases, this is a highly recommended thing. Again, post that, we also did some optimizations in the tail latency optimization. So as I talked about, there's a periodic flush operation. And the flush operations happens on multiple thread pools, like there is a dedicated thread pool for flushes. And write pools, right, they can also contribute to flushes. But if you have a use case where you may not want the data to be very immediately available, right, you can offload that work from the write pool and always have the flush pool do it. So what it ensures is your critical write path remains unblocked with these flush operations. And in the background, they'll keep happening, which will again provide you some improvement in tail latency. And you can use the write pools for the actual work, which is the writes. Again, this is an opt-in index setting. So yeah, these were the few optimizations we have done. And we are also exploring few use cases, as some of them are in progress already, and some may or may not. I'm not sure, but as OpenSearch 3 RC is happening, right, some of them may be going. So a few of the problems we have explored in the past few months itself, right? One is the improvements around vector search, like how can we improve the latency for queries there, and also maybe the relevance of results. Then the storage and throughput and latency. So one of the RFCs that is actively getting discussed in OpenSearch community, right, is the context-aware segment. So think of it like this, right? If you are aware of basically the data in OpenSearch, it gets positioned to be seen in something called segments. And there are multiple segments, and all of them may contain data in the order in which the data arrives, right? So if we can, during the ingestion process, divide the data into segments based on how they're going to be queried. So for example, let's say you have status codes while you are ingesting the data, right? So if you can keep all the 200 status codes together, 400 status codes together, and 500 status codes together, right? And then you want to query just errors, you know that you don't have to visit the entire data set. You can just go to the 500 and 400, that will give you the errors. So in general, for web access logs, right, you will have millions of 200s and thousands of 400 and 500 status codes. So context-aware segments, what it does is it divides the data according to the query that you may be performing. You can configure that in indexing time. And then during query, you just have to visit those thousands of documents rather than the millions of documents you would have otherwise visited. It also helps with relevance and performance of the vector search queries. So if you know that, OK, your data belongs to certain tenants, right, as you are making your queries. So during indexing, if you can divide your data into different segments according to the tenants you have, you can serve basically, you don't have to apply filter queries for the HNSW graphs that were created for them, right? You can it will just have the segment will just have all the information you need to query that tenant and will provide you more relevant results. So approximate kn search and all those things work well with this as well. And also for the search kind of use cases, right? So if you attended yesterday's talk on improvement of aggregation performance, you would recall that it helped. Basically, we had an optimization of numeric, basically using the BKD trees or the points index. So with context aware, you can use them with more filters as well. The next thing we are working on is the derived source, and the PR for this is already in progress. So this essentially what it does is this entire source field that we used to store, which I talked about, used 40% of the storage almost. This essentially gets rid of that and helps you derive the source on fly. And with this feature, what we have seen is for the logs kind of use case, the throughput improvements is almost of the order of 22%, and storage reduction is almost 27 to 30%. And for example, we were analyzing a vector use case around which had 10,000 documents and 128 dimensions, and from 24 MB, the data came to only 10 MB. So it helps significantly in reducing the storage size. One more thing, if you attended the talk in the morning, so start tree indexes, I think, is already covered, so I'll skip this now, but it helps very well with the aggregation queries just by deciding at the time of indexing what data structure you want to create. And the other thing is the append-only indices. So as I talked about, there is a live docs file which stores the deleted documents. And when you have to figure out which documents are applicable for your queries, you always need to filter out deleted documents. And some data structures, they suffer a lot due to these deleted documents. So in case you are already aware that you are not going to have deletes in your indices, right, you can configure at the indexing time that your index is an append only. And behind the scenes, all the optimizations and data structures that are applicable for them will be essentially available for you to use. So this very well helps with all the use cases. And for example, start tree itself, right? It needs to rely on append-only indices because with deletes, the reduced documents that are there, they may not be applicable, and hence the queries may not benefit that much without append-only. So I talked about a lot of features, and essentially, we do see a lot of adoption challenges for these features, right? Most of you may be hearing these for a lot of these features for the first time, but they have been around in OpenSearch for a year or so. And there are a variety of use cases, a lot of knobs, and basically we require a lot of knowledge to essentially use these features, right? So in order to help with adoption, we have also introduced something called as ABC templates. So for example, let's say you had to configure a metrics index, so you would have to go say that this is the codec, this is a merge policy, this is a refresh interval, this is a replication type, and some other optimizations, right? With the templates, all you have to do now is you can just provide the context of the use case for which you are building the index, right? And what it will do is behind the scenes, based on the context you choose, it will essentially apply all of these settings for you so that you can get the best performance out of the box. And yeah, so I've put a QR as well for if you want to visit the documentation and blog for this, but which will give you more information about how you can use them. But just to give a few pointers, right? These templates are versioned so that you can choose which basically features you want or not. By default, any new things that get added to these templates will be available to you, but you can choose to restrict them also. In that sense, it's a managed experience which is available to you out of the box. And we also plan to add more parameterization support on these templates so that if you want, you can basically play around with the values you may want in a smaller sense as well. Yeah. So these are the few use cases which we have already onboarded to the template. So for example, logs, metrics, Nginx logs, Kubernetes logs, Apache Web logs, and few of the Amazon service-related logs which are already onboarded. And you can choose to contribute and add more use cases that you feel may be needed for you, and will help you basically take that to pay forward to the community as well. So yeah, that's on the what use cases we have onboarded. And one more good thing is if you are aware of the OpenSearch integrations for dashboards, right? We already, basically these work very well with that. And once you create this index, you can just use one click to create your dashboards as well for these indices. Yeah, just for future, I think few of the things that we are looking actively at is mostly around few of the ingestion formats. Like JSON parsing, as I talked about, is a very expensive operation. How we can mostly use more binary protocols and see how to improve the data performance. And also mostly few things on the disk interaction optimizations on how we can compress or encode the data structures better as well. So these are the few things we are actively working on, and we'll put RFCs out for that as well. And I invite community for active discussions on any of the RFCs that we have, and looking forward to any questions now. Yeah.
Thank you very much. I think we have time for one question. So anybody? All right, there we go.
I think I catch that you were able to improve the indexing, obviously, but I was wondering about the refresh interval. Mm-hmm. Were you able to perhaps like reduce the refresh interval with the improvements that you saw after your indexing improvements were put through?
Yeah, so for example, as part of refresh, all the on-disk data structures get created. So once we get rid of the actual source and introduce derived source, right, the actual latency for the refresh operation has come down. So few of the things have helped there. So I think still we support a minimum of 1 second refresh interval. And the time it takes to refresh is basically significantly reducing as well with some of the optimizations that we have done. For example, because if now you have derived source, you don't need to actually compress the data and write to disk. So you get rid of that 40% chunk of the actual indexing work that you had to do at the refresh time, right? So few of those things have helped with the actual refresh latencies. And there are few things as well which we are exploring if may help out or not. But we'll put them on the community in the GitHub issues as well and share.
All right, thank you very much. Everyone, another round of applause. And,